All right, last video to practice more with position, velocity, acceleration. Now knowing what we know about integrals, not only can we go forwards and going from position, velocity to acceleration, but we can go backwards from acceleration to velocity to position. So let's read number one. We'll do two out of these three problems in this video, and then we'll pause and we'll practice more in class. There's a coin. We're dropping it from an 850-foot building. The velocity of the coin is given by that equation. Find both the position function and the acceleration function. All right. Well, which one would be easier to find first? I guess I can find the acceleration because the acceleration is just the derivative of the velocity function. And the derivative of negative 32t would be negative 32. I'm done. I need to find the position function. The position function is the antiderivative of the velocity. And so if I do that, I'm going to take the antiderivative of this, which would be negative 32 times t squared over 2 plus c. Excuse me. Yes, I can reduce this to negative 16t. So why don't I do that now? Negative 16t squared plus c. However, I need to figure out what that c is. I can't just leave it as a generic position function. And luckily, I know that the initial position was 850 feet. So 850 feet was the position at time zero when they dropped it, because they dropped it from an 850-foot building. So if I substitute 0 in there, that's going to be gone. So that means C does, in fact, equal 850. So I can erase this and put an 850 there. And now I have my position function. And I had already found my acceleration function over here. So I started from velocity. I took the derivative. I got the acceleration. I started from velocity. I took the antiderivative or the integral, and I found the position function. And I used the initial condition, meaning the piece of information, the very specific particular piece of information, to get the exact position function. That's number one. Let's do number two. Yeah, let's do number two, and then we'll just not worry about number three. If you want to do number three, you can work on it and then bring it to class and we can check it. But number two, there's a particle moving along the y-axis. So instead of moving left and right, it's moving up and down with an acceleration of a of t equals 2, where t is time in seconds. Okay, the acceleration's velocity at time 2 is 5 centimeters per second. The position of the function at time 2 is 10 centimeters. What is the position of the particle at time 6? All right. There's a lot. So let's think about what we want. We want the position, but not the position function, the position at a specific moment in time. But because I'm starting with acceleration, I need to find the antiderivative of acceleration, which is going to give us to velocity. So velocity is going to be the antiderivative or the integral of acceleration, and that's going to be 2t plus c. However, I need to know what that c is. Luckily, they told me that the velocity at time 2 is 5. So the velocity is 5 at times time 2. And that means c has to equal 1. So I'm going to come over here and say, okay, so now I know from all of this that the velocity is 2t plus 1. Now I'm going to solve what they're really asking for, which is the position. But I needed the velocity equation in order to do that. But notice, since I'm not looking for the position function, I'm looking for a position at a precise moment, and they give me another one, then I can use that fundamental theorem and accumulation to figure this out. So here's what we know. We know that the position, and I'm going to use x. Actually, let's use y because it's going up and down, right? So I know y at time 2, and I'm going to find the integral of v of t from time 2 to time 6, and that's going to give me y of 6. Now let's think about what this is saying. We know the position at time 2. We're going to find the displacement from time 2 to 6 and add it on so that it can give us the position, the final position at time 6. I'm starting with where I know it is at the beginning. I'm adding on how much it changed, and it's going to tell me where I'm going to end up. Great. Well, I know y of 2 is 10. And everything else I can figure out using my calculator. Or I can just do it by hand. And I haven't done one by hand in a while, so maybe I can do this one. 2t plus 1 dt. Well, this is an easy one because the antiderivative of this would be t squared plus t evaluated from 2 to 6. And we're going to add on to 10, and that's going to give us the position at time 6. So in order to figure that out, substitute the 6, substitute the 2, and subtract those. And whatever answer I get, I'm going to add it on to 10. This is 42, and this is 6. 42 minus 6 is 36. And if I add it on to 10, that's going to be 46. That's the final position. I shouldn't say final position, but I should say the position at time 6. That's what we were looking for on letter B, and we were able to find it. Notice when it's asking, or when you're looking for a function, you're going to get that plus c. You got to find that plus c. But when you're looking for a specific value at a given moment in time, perhaps you can use the accumulation property here of the integral in order to figure out. And this is really the part of the first part. This is the first part of the fundamental theorem of calculus right here that can help us find the answer maybe a little bit quicker. And that's what you need to know about motion going backwards using definite integrals.